Hello, I'm going to talk about visual stress in the workplace. We've created a visually toxic world in terms of flicker, in terms of patterns, and in terms of local colour contrast. And I'm going to deal with each of these in turn, beginning with flicker. In the natural world, there is little flicker. The sun doesn't flicker except when it's reflected from waves or interrupted by the leaves of trees. Otherwise, the only variation is during the day. Very slow. In the artificial world, lighting is from electrical supply, the alternating current supply, and then there is nearly always flicker of some kind. With incandescent lamps, the hot filament retains the light from one half cycle of the mains to the next. So the flicker is relatively small, about 5% or so, whereas with fluorescent lighting, the gas discharge happens twice with the electricity supply, and the variation is at 100 hertz or 120 hertz, and the amount of variation is somewhere between 30 and 100% flicker. We know this causes headaches. In 1989 we showed that modulation of 35% at 100 hertz was enough to cause headaches in office workers, even though they didn't know that was happening. It was a double-masked study. Later, the circuitry controlling the lamps was changed. Electronic circuitry was introduced, and that reduced the flicker down to the same levels, roughly, as incandescent lamps. And then compact fluorescent lamps were introduced, and although they had electronic circuitry, there was still quite a bit of flicker, up to about 30%, and that contributed to the dislike of this product. And then LED lamps were introduced. Now, the flicker from those lamps depends entirely on the electronic circuitry in the base of the lamp. Sometimes the lamps flicker 100%, sometimes they don't flicker at all, and you can't tell before purchase whether or not they're going to flicker. And the lamps that flicker cost no less than the lamps that don't. So there is no cost incentive to purchasing lamps that flicker, and we would be much better off purchasing those that don't flicker. Now, the variation in speed of flicker until recently was, as I say, at about twice the frequency of the main supply. But with LEDs, the flicker frequency can be much higher, depending on the electronics. And recently we've shown that flicker can have perceptual effects up to 11 kilohertz. And that's because when the eyes make a saccade, they move extremely rapidly, up to about 180 degrees a second. And people can see flicker during a saccade as a pattern. If you move a flickering lamp across the visual field, you'll see a pattern. And that's what you see when you move your eyes at night across the tail lamps of cars, if they're LED lamps. Now, some people can see this pattern from the flicker at 6 kilohertz. But interestingly, people who experience visual discomfort in everyday life can see the pattern at 11 kilohertz. They're much more sensitive to it. Why should there be this relationship between sensitivity to the pattern on the one hand and symptoms of visual discomfort? Well, it may be because the brain uses the visual smear during a saccade to guide the eye movements, to guide the next eye movement. So flicker at high frequencies might interfere with eye movements. We don't know yet, but it seems possible. So flicker then has many properties, mainly at twice the frequency of the supply, electricity supply, but also at higher frequencies as well. And all of these are potentially problematic. Now I'm going to consider patterns. Within nature, we have very few patterns. And in general, the brightness of a point in space is very similar to the brightness of a neighbouring point in space. Two points that are close together have similar brightness, whereas those that are further apart can have very different brightnesses. And there's a relationship between contrast on the one hand and separation on the other. And that can be expressed using Fourier analysis. And it's referred to as 1 upon f. And that's a property of all images from nature. And it's something that the brain has evolved to take advantage of. Because the brain is a very expensive organ to run. It weighs about 2% of body weight, but it consumes about 20% of body energy. It's enormously expensive to run, and so we can only afford to run a few neurons at any one time. And the coding in the brain takes advantage of the property of natural images that we've evolved to deal with by coding so that you take advantage of the 1 upon f coding. That is to say, the coding is designed for natural images. But if we look at unnatural images, there are repetitive patterns at every spatial scale. And that interferes with the 1 upon f relationship that the brain expects. And so the brain works harder, uses more metabolic energy in order to see images of this kind. And there are stripes everywhere, and they're getting worse. This is some modern architecture from Bahrain. And it's not only the exteriors of buildings, but the interiors. You can see the stripes in the Louvres here of the lighting from the windows and so forth. Stripes from the blinds, shadows, banisters and so forth. Now, stripes are sometimes a necessary feature of design if you're using modular construction, but all too often they're a totally unnecessary feature of design. This is when stripes are used by designers simply because of the effects they have. And some of the effects they have are really unpleasant. I'm going to show you now a really unpleasant pattern. If you have migraine or photosensitive epilepsy or photophobia or visual stress, I suggest you don't look at this pattern. Please look away or cover one eye. If you want to look at the pattern, I suggest you do so simply by closing one eye. That's what I'm going to do. I'm only going to show the pattern for 3 seconds because it is, frankly, epileptogenic. Are you ready? That pattern is everywhere. It's not usually, the patterns in the world around us are not usually quite as bad as that, but they are everywhere, not only in grills and gratings, on clothing, in furnishings, on walls. And it's not only stripes that are a problem. There's a condition called trypophobia, which we described, in which people are averse to patterns of dots, holes particularly, and they find them nauseating. Now, what is it about repetitive patterns that makes them nasty? Well, a lot depends on the viewing distance, because that determines the size of the pattern on the retina. The angular subtense of the pattern determines the area of the visual cortex to which the pattern projects, and that's the critical feature. Another important aspect of the pattern is its spatial frequency. The number of pattern elements, or cycles of the pattern, in 1 degree visual angle. So again, that's critically dependent on viewing distance. The worst patterns have a spatial frequency of about 3 cycles per degree, which is where the visual system is most sensitive in general. But there are aspects of a pattern that are independent of viewing distance, and one of these is the contrast. Now, this is the pattern I showed you earlier, but I've reduced the contrast down to about 5%. And you can see it doesn't have any nasty effects at all. It's innocuous. Whereas if we increase the contrast just a little bit, 10%, then it's just enough to start causing problems. But we can have patterns at high contrast that are also no problem at all. This is the pattern I showed you earlier, but I've made the lines thinner. So the duty cycle of the pattern has been changed. 50% duty cycle is worse. That's when the pattern's lines have the same width as the separation between them. This, of course, pattern isn't a problem because the lines are so thin. But there is a pattern that we look at every day that has a 50% or thereabouts duty cycle, and that is text. You have to look at text, can't avert your gaze, and the stripes of text, the horizontal lines here, can be a problem. That's why it's so important to space the lines of text to make them clear. But of course there's not only horizontal lines from text, there are also vertical lines. Now Times and Palatino and other fonts of that kind have very regular spacing of the vertical letter strokes, and we know that that gets in the way of reading speed. It interferes with the way in which the eyes come together after each eye movement during reading. The eyes have to be realigned, and that realignment takes longer when the font is striped like this. And there are other stripes in other types of reading. Publishers produce music manuscript with a width of the lines that varies considerably. The stave is always the same size, but the component lines varies considerably. So some can be 0.1 millimeters in width and some can be 0.4 millimeters in width, and it makes a difference. There are twice as many sight reading errors when you try and sight read music that has a thick stave. So that is my whistle-stop tour through patterns, why they're nasty, when they're nasty. Now I'm going on to colour contrast. And I'm going to introduce this with a picture of a barn by an artist that I know called Debbie Ailes. She created a pattern based upon this barn as a result of her migraine attacks. And that inspired this painting, which obtained a prize for representation of migraine. And you can see that it's unpleasant to look at. It's unpleasant because, as we shall see, the colour contrast is very unnatural. So once again, the brain is having to work hard. In fact, we've demonstrated that. People have been asked to rate works of art, and the most uncomfortable ones are those in which there is a large variation in local colour contrast. We've evolved a little model whereby you can take each pixel and measure the colour difference between that pixel and its neighbours, and you average that for all the neighbouring pixels, and then you average it over the whole image, and that gives you one number, which predicts how uncomfortable that work of art will be to look at, predicts the ratings of discomfort. So we can predict discomfort now from its colour, the spatial frequency of the image, its size, its contrast, and whether there is flicker or not. Now, susceptibility to visual stress of this kind varies enormously in the general population. About 10% of the population are totally unaffected. You show them an nasty pattern and they wonder what you're talking about. Whereas those in the population who have neurological differences are disproportionately affected, maybe about 10-20%, particularly those with migraine. So in these neurodiverse populations, we know that they're particularly susceptible to visual stress. So, for example, migraine, particularly migraine with aura, autism, head injury, stroke, multiple sclerosis, photosensitive epilepsy, visual snow, and cluster headache. Fortunately, we can treat most of these disorders, the photophobia that accompanies them anyway, and we can treat that using coloured glasses. What we do is we ask the individual to look at text in a box that illuminates the text with coloured light, and in which the colours can be varied systematically from white to strongly coloured and back to white. And we explore colours systematically like this until we find an optimal colour using a hill climbing technique, effectively, and then we offer that colour using just two dyes and two neighbouring dyes in this diagram, and we can build up trial lenses, ratify the tint, and then make the tint into tinted lenses. And we find those tinted lenses reduce the problems that these patients have. Why should they work? Well, coloured filters will reduce colour contrast. And it doesn't matter, any colour will do so up to a point. But of course, different people choose different colours. Here are two studies. This is from Amelia Aldridge et al., and this is from Alexandra Rivera, different samples of patients. These are controls. They choose a colour for reading that is close to the daylight locus. So they choose a colour that is very similar to the one they would normally experience, whether it's a blue of daylight or a yellow of incandescent light. Whereas patients who have migraine with aura tend to choose strongly coloured lights well away from the daylight locus. So we've created a visually toxic world in terms of flicker, patterns, and colour contrast. We can treat some of the problems using tinted glasses, but much better to prevent the problems in the first place. So how can we do that? We can use slow-mo to check the electronic ballast of LED lighting. LED lighting has an enormous variety of different ballasts. Some flicker, some don't. And as a first test, you can take a smartphone and take a movie using slow-mo and play it back. And if you play it back, you can see the flicker quite easily from some LED lamps. Of course, that won't deal with the high-frequency flicker, but it will deal with the 100 per second flicker. We can avoid unnecessary stripes from, for example, Venetian blinds, using a different type of blind with lower spatial frequency and a lower duty cycle. We can take rubber mats and make sure that the contrast of the mat is low. So, for example, make sure that you don't put a black mat with holes in on a white marble surface. You can use modest colour contrast on walls and surfaces, and you can space lines of text and avoid spatially repetitive fonts. Thank you.